Hey everyone, how's everyone doing? Hope you're all doing well. Welcome. This will be part of a mini series where I'll be covering maths, chemistry, and physics topics and condensing them to short videos for your leisure. In this video, we'll be going through Gravity and Motion 1, and we'll be covering gravitation, Newton's law of universal gravitation, gravitational fields, conservation of energy, and motion on inclined planes. Before getting started, I highly recommend downloading the notes in the bio below so that you can annotate and follow through the video. So gravity and motion. Looking at Newton's law of universal gravitation, this is basically the force of attraction between any two mass bodies. So the force is proportional to the product of their masses and inversely proportional to the square of their distance apart. So in layman's terms, this is the equation here. So force is equal to G. Big G is the universal gravitational constant, and it's always a constant. It's given by 6.67 times 10 to negative 11. So just remember that. It's also in your formula sheet. And then the mass of body 1 and the mass of body 2 over r squared. And r squared, to note, is the distance between the centers of the mass of the two bodies. So not from the surfaces, but from literally the centers. Always remember that. You're doing a force of attraction question. So like I said before, basically this is just the force of attraction between any two mass bodies. So ideally speaking, this also applies to, I guess, people, day-to-day people. So let's say you have two people standing next to each other. Technically speaking, there is a force of attraction between the two of them. However, just because their masses are very small, the force is going to be quite negligible. So here in the diagram below, you can see that this is showing it's illustrating the force of attraction between the Earth as the moon orbits around the Earth. All right, two mass bodies, distance apart, and have relatively high masses. So therefore, there is a force of attraction, and you can calculate that. So before moving further, there's a bit of jargon terminology that we should probably get our head around. So mass is the amount of matter in a body and is measured in kilograms. The mass remains unchanged with different gravitational fields. So whereas weight is a force and measured in newtons, it is a product of your mass and the gravitational field strength you are exposed to. And the equation is given as weight is equal to mass times gravity. Your weight would be greater standing on the surface of the Earth versus the moon, as Earth's gravitational field strength, G, is greater than the moon's. So just reiterating, the difference between mass and weight is mass is always going to be the same, no matter what surface you're on. Weight is basically a product of mass, right? So it's basically the mass multiplied by the gravitational field or acceleration that you're feeling on wherever you're standing. And weight is measured in newtons because it's a force. You also have center of mass, or COM. This can be basically conceptualized as the single point in a body about which a mass is evenly distributed. It is also the point at which objects will smoothly rotate. So think of, whereas center of gravity, or COG, can be considered the same as center of mass in all aspects, however for weight instead of mass. So moving on to gravitational fields. So key thing is all bodies of mass will have its own gravitational field, denoted by small g. The field is responsible for the gravitational force of attraction between mass bodies. This is what gives rise to basically that force of attraction. So here you have an example of, let's say that's Earth, and these are basically the gravitational field lines coming into Earth. So the way we can calculate lowercase g, or gravitational field strength, or acceleration, is given by the equation below. So small g is equal to big G. Once again, big G is just the gravitational constant, multiplied by the mass of the body divided by r squared. And r is literally the distance between the center of mass of the body and the center of mass of the other object. So let's say, for example, you're on top of the surface, right? So it's the distance between the center of mass of the Earth to the center of mass of your body. Or if you were floating in space, it'd be from the center of mass of the Earth to, I guess, the center of mass of your body in space, at that distance in space. So variations of the value of G, for example, the Earth. See, on the Earth's surface, the value of G slightly varies around the surface of the Earth due to the Earth's uneven shape, i.e. the troughs and peaks geographically. So it's probably, this question actually does come up in assessments and whatnot. So that's always good to know. And as we go into space, as we leave Earth's surface, the value of G decreases in proportions to the square of the distance from its center. For example, you can derive proportion relationships from the equation here, where you can see that the gravitation field strength is inversely proportional to r squared, meaning that as you increase your r, as you step further away from the mass body that has the gravity field, the lesser the effects of that gravity field, the lower the gravitational field strength you'll be experiencing. And it's actually a squared relationship, so it actually happens even faster. So for example, this is probably a good diagram to illustrate. Let's say this is a person, and on the surface of the Earth, they're basically experiencing let's just say that much amount of gravitational field strength, but then as they get further and further away, it gets lesser and lesser. So for example, 9.8 on the surface of the Earth, a radius of 2r will be a quarter of 9.8, and the radius of 3r will be 1/9 of 9.8. So those factors come into play because, once again, the relationship is r squared in that formula. So moving on to conservation of energy, you guys might have learned this in year 11 or maybe even year 10. Basically, the conservation of energy states that in an ideal world, energy cannot be created or destroyed. It is purely converted to other forms of energy. So obviously, in the real world, we actually have inefficiencies, and we actually do lose energy for all intents and purposes. In physics, when we do questions, we assume that it's an ideal world, it's a perfect world, and we don't lose energy, and instead it's converted. So that means we can actually form the relationship. This can be illustrated by the relationship below. So total energy before should equal to total energy after, even if energy is converted, right? Or E1 is equal to E2, where 1 denotes before and 2 denotes after. You can further break this down to kinetic energy and gravitational potential energy. So half mv squared representing kinetic energy and mgh representing a gravitational potential energy. Obviously, before has to equal to after as well. One thing to call out as well, the work function. So work is equal to force times displacement is interchangeable and is equal to energy. So what I'm trying to get at is every time you see work is always interchangeable with energy in physics. That's because they share the same units, joules. Cool, just one thing to note. So applying this notion to a question, we've got a popular amusement park ride is the loop-the-loop. So it's basically this guy here, in which a car descends a steep incline at point X, enters a circular loop at point Y, and makes one complete revolution of the circular loop. A car whose total mass is 500 kilograms carries the passengers at a speed of 2 meters per second. So it starts off with 2 meters per second when it begins its descent at point X and has a vertical height of 50 meters. Question is, calculate the speed of the cart at point Y. So you want to be calculating the speed at point Y. And also, what is the speed of the cart at point Z? So when it's midway doing its loop-to-loop. So let's get into it. Cool. So for A, we're calculating the speed of the cart at point Y. So if you think about it, you can break this question down into two situations, right? So that would be point 1. So that would be cart at point 1, so before. And this would be cart at point 2, so after, all right? So from what we learned before with conservation of energy, we can write a relationship. We can go E1 is equal to E2 is equal to E2. All right. We can further break this down to the kinetic energy and gravitational energy constituents, right? So we can literally write the kinetic energy before, and I'm basically denoting all the values that pertain to point 1 as 1, and obviously the after I'll denote as 2. Alrighty, so we're actually being asked, what is this? Calculate the speed of the cart at point Y. So that would be, we're looking for this V. V2 essentially will be the speed at point Y because that's the point 2. So that's where the cart is at point 2. So let's start filling this out. Actually, before we start filling this out, we can do a neat trick. So M is actually constant throughout this whole equation, which means that we can actually just eliminate that real quick, because technically what you're doing is you're just dividing everything by M. So we can just get rid of that just for the sake, just to simplify things. I might just rearrange this as well, just to make it a bit more simple. So bear with me as I try to. Furthermore, at point Y, the height is technically 0 relative to the ground. So that means that this value here is actually 0, and anything multiplied by 0 is effectively just 0. So I'm just gonna cross that out because h is equal to 0 at that point. Cool. So now we can start filling our things out. So I think just to simplify things, I'm going to rearrange this in terms of V2, right? So bear with me. So we have V2 squared is equal to 2 Cool. And then you've got, oh, technically we can simplify this further. So you can have is equal to, so the half disappears, you're left with v squared plus 2gh1. And to get rid of the square, you want to square root the whole thing. So square root the whole thing, you've got v1 squared plus 2gh1. All right, and all you have to do is just start filling it in. So that's equal to, so we know that at v1, so at point x or point 1, we know that it has a total velocity of 2 meters per second. So 2 squared plus 2. We always take gravity on Earth as 9.8, and it's given in your formula sheet as well. And the height at point 1 is 50 meters, so we put 50 meters. Great. So now if we punch that in the calculator, so now when we punch that in the calculator, we get we get 31.4 meters per second. Awesome. We get 31.4 meters per second at point Y. All right. So what effectively is happening is we're still conserving the energy. So what effectively is happening in this scenario is at point 1 and point 2, from point 1 to point 2, we're still conserving the energy. At the beginning, it has max potential energy, right? And it has, a small speed, a relatively slow speed, right? Obviously, so it has a small value for kinetic energy and a large value for potential energy. But as the car goes through its course and goes to Y or point 2, both of these ultimately start becoming maximum kinetic energy. And that's because we lose all that potential energy. So both of these sum up to this essentially. That's why velocity is a lot greater at point Y than it is at point X. So moving on with question B, we've got what is the speed of the car at point Z? So very similar, we're going to use the conservation of energy. So total energy before equals total energy after. So 1 is equal to E2. You guys can put before or after. It's the same thing. We'll stick to one denotation. So same thing again. So you got half mv squared. So same thing again, but this time your E1 will be at point X and your E2, your scenario 2, will be at point Z. Right? So at E1, it's half mv squared plus mgh1 is equal to half mv squared 2 plus mgh2. All right. So once again, you can cross out the m's, which is really handy. Cool. And now we're trying to basically solve for v again, so v2 again. In this case, I'll rearrange just for simplicity. So you got v2 squared is equal to 2 half to v1 squared plus gh1, take away gh2. All right, and that is equal to v1 squared plus 2gh1 minus 2gh2. And then getting rid of the square, we square root the whole thing. And we get v1 squared plus 2gh1, take away 2gh2. All right, now just putting in our numbers. So v1, once again, it's just 2 meters per second. So we can just put that in. Plus, we've got 2 multiplied by, once again, gravity is always taken as 9.8. At height 1, it's at 50 meters. 50 meters. Make that a bit longer. Take away 9.8. Now, this is the fun bit, right? So at point 2 or at point Z, what is the height of the card? So we can actually calculate that pretty easily. So we know that this is 50 meters. We can actually calculate that pretty easily. So we're given the radius of this circle, right? So technically where it's positioned at, it's just the diameter. So all you have to do is just multiply 15 meters by 2 to get the diameter, which is basically the height of that card off the ground. So that would be just 30 meters. Awesome. So if we punch that in the calculator, we get 4 plus 2 times 9.8 times 50. Take away 2 times 9.8 times 30. Awesome. And we get a value of 19.9 meters per second at point Z. So, which kind of makes sense. So once again, you'd expect to have a higher value, a higher speed or higher kinetic energy at point Y because there's absolutely no height. But the moment there's height again, you'll start losing kinetic energy and therefore your velocity will start going down as well. Cool, hopefully that makes sense. So next is motion on inclined planes. So effectively an inclined plane is, think of a wedge or a ramp and you basically have a body on it, right? And obviously due to gravity, it might slide, it might not slide. So one of the things to note is direction of a gravitational force is always towards the center of the earth that is vertically downward. So mg, obviously force due to gravity or weight force. Bodies can move down an inclined plane due to the effects of gravity. So with the weight force, it actually has a horizontal component parallel that is parallel with the plane, right? Which actually might make it slip if there's not an opposite force counteracting it. Since forces are vectorial in nature, we can break down the force by its perpendicular and parallel components, as seen below. So we'll get into it in a bit. So tools to hack. The key to solving inclined plane questions is to 1. Pick an axis to break your forces into, so either the parallel and perpendicular to the ramp or conventional XYZ axis, or the conventional XY axes. So first nominate a axis you want to work in, so either the XY axis, so your typical conventional XY axes, or going with the axes of the inclined plane. In this case, it would literally be the perpendicular axis would be this way, and the parallel axis would be this way. It's just basically a conventional XY axis sort of rotated to fit that plane. But what's important is you need to break all your forces that don't adhere to your chosen axes. So let's say we chose the parallel and perpendicular axes relative to the plane. We want all our forces to adhere to those two axes, right? So technically speaking, your normal force is already on that axis, which is great. You don't have to do anything. Your frictional force is also in that direction, on that axis, so that's all good too. The only force that you need to break up in this case is your weight force or your gravitational force going down, right? Because it doesn't adhere to the perpendicular and parallel axes of relative to this plane. So you want to break this down to its horizontal and vertical components. So technically these two vectors added together actually give the mg. So they've already done it for you in this case. So then you do the sum of forces. So you do it in the vertical direction and also you do it in the horizontal direction. So using what we know about bodies in equilibrium, sum of forces, choose either horizontal or vertical, and basically this is how you write it out. In this specific case, if you do sum of forces in the vertical, so when I say about vertical, we're talking about literally in this direction, so this axis, the perpendicular axis. So we're taking up as positive and down as negative. So n, the sum of vertical forces is equal to 0 because we're assuming that it's static, it's not moving, and that the positive vertical forces and negative vertical forces basically cancel each other out and equal to 0. So therefore it's not moving up or down. So in this case, anything up is positive. So n, take away mg cos theta because mg cos theta is in the other direction, and basically you can solve. And then you also do it in the horizontal direction. So once again, equal to 0 because we're assuming it's static, it's not moving left or right, and that the forces going to the left, forces going to the right actually cancel out each other, are equal to each other. So in this case, we're taking anything to the right as positive, as you can see from there, f take away, and anything from the anything to the left as negative. So it's f take away mg sine theta. So f take away this should equal to 0, and then you can solve. All right, and if that meant nothing to you at all, we'll get into a question to see how we can use that. So you've got a block of mass of 2.7 kilograms is placed on an inclined plane whose incline is 22.5 degrees to the horizontal. Determine. So let me just zoom out so I can draw something. So I always like drawing a free body diagram. I can basically visualize it myself and also tell the marker, let the marker know that I know what I'm doing. So let me draw my inclined plane, my free body diagram. I'll make it quite big, so for the purpose of visualizing this. And you've got your block of mass in the middle there, and let's draw your weight force going down. W is equal to mg, and you've also got a normal force going up. Bang. So once again, the question is asking, determine the weight components acting parallel and perpendicular to the plane. So once again, you want to first nominate an axis for your inclined plane. In this case, the question's kind of sort of leaning in. The question is sort of nominating which axis we choose, and that's the one that's parallel and perpendicular to the plane. So this is what the axes will look like. Cool. So anything up in that direction is positive, anything to the right is positive. Cool. So the question is, determine the weight components acting parallel and perpendicular to the plane, right? Once again, so this is the axis that we've nominated. The only force that's not adhering to that axis is the weight force, right? So we need to break this up into its horizontal and vertical components so it suits these axes, right? So let's break this up. So basically just vectors, right? So you've got a horizontal force in that direction. Cool. I'm just going to call that weight h, small h. Cool, in the horizontal. And then you've obviously got weight vertical. All right, that's obviously 90 degrees. Great. Oh, one thing I forgot to draw is that there's an angle here. It's given by 22.5 degrees. Cool. So now we've broken up our weight force into its horizontal and vertical constituents, right? And it's asking to determine the weight components acting. So we actually have to do a calculation. So let's see if my pen will do what it needs to do. So using similar triangles, we can also actually determine that this angle here. So using similar triangles, we can actually also determine this angle here is actually 22.5 degrees, right? So let's find the weight components. Let's find WH first, right? So for example, looking at WH relative to that angle, that's the opposite. Obviously the weight force mg is your hypotenuse. So that means we can use sine. We can derive a relationship using sine. So sine 22.5 is equal to WH over mg. And then WH is equal to mg sine 22.5. Just filling that in, the block of mass is 2.7. Gravity is always 9.8. Sine 2.5. And punching that in the calculator, we get 2.7 times 9.8 times sine 2.5. We get 10.1 newtons, all right? For the weight, we get 10.1 newtons for the horizontal weight component. So very similarly, you can also derive a relationship for WV using trig, exactly the same. So I might just write it out real quick. Obviously WV in this case relative to the angle is the adjacent, so we're using cos. So we've got mg cos 22.5 is equal to 2.7, 9.8, and then cos 22.5, right? And that gives us 2.7 times 9.8 times cos 22.5. That gives us a value of 24.4 newtons, right? So the vertical weight component is 24.4 newtons. Cool. So next question is, the plank is slightly rough and the block remains at rest on the plank. What is the minimum force of friction needed for this to occur? So having a look at our diagram again, you've basically got frictional forces acting, preventing it from slipping down, right? So that frictional force will act in this direction as to prevent it from slipping downwards. So frictional force, and the only thing that's actually counteracting that frictional force is the horizontal component of the weight force, right? So technically speaking, if the question was what is the minimum force of friction needed for this to occur, for it to for the block to remain at rest, all you would need to do is to counteract this force, the horizontal weight component force, right? So technically speaking, the minimum frictional force required is just 10.1 newtons because it has to cancel that out, right? So anything less, it will start slipping. Anything more, it'll stay, or it might even go up. Cool. So hopefully that makes sense. So moving on to C. Assuming that the force of friction is reduced to 10% of the weight force, determine the net force acting on the block. So let's say, for example, it's the frictional force is no longer 10.1, but 10% of that, right? So 10% of that is going to be 1.01. So let's just say frictional force is equal to 1.01 now, right, in that direction. And we're trying to find the net force. So now, because your frictional force is just 1.01 newtons going to the right, your net force effectively on the block is just going to be F net is equal to, you still have your weight force as 10.1, right? And we've taken everything to the right as positive. So obviously the frictional force is in that direction. So you go 1.01, take away the horizontal component of the weight force, which is 10.1, right? Which gives you negative 9.09 newtons going to the left. So it is slipping, right? And the question B is part 2 of C, the acceleration of the block down the plane, right? So with acceleration, we know the F net already. So we have the formula F is equal to ma. Now let's rearrange that for acceleration. That's going to be F net over A, F net over m, so that would equal to 9.09 over 2.7, giving us an acceleration of 3.37 meters per second squared. So basically, if the frictional force hypothetically was only 10% of what it was before, obviously the block will start slipping because the horizontal weight component is a lot larger than that. It will start slipping. As it starts slipping, obviously it will start accelerating, and that is the acceleration. Well, hopefully that makes sense. And that sums up this video. Hopefully you guys found it interesting and took something out of it. Once again, recommend downloading the notes in the bio below, and I'll catch you in the next one. Cheers.